Hello, we're working in section 3.5, implicit differentiation. First, let's make sure we remember and understand what we mean by Leibniz notation. So if I write derivative with respect to x of x, that's just another way of writing x prime. Derivative of x with respect to x, where x prime is 1. We're going to start using this notation almost exclusively because it's going to become very important. What's the independent variable and what's the dependent variable, and what variable are we differentiating with respect to? That will become more obvious in the next few sections, but there's a reason kind of to get away from the prime notation all the time and to start using this Leibniz notation. So let's just look at the Leibniz notation a little bit more. Derivative with respect to x of x cubed. This is how I would write the derivative of x cubed using Leibniz notation, and I know that's 3x squared. But what if I wanted the derivative with respect to x of y? Well, without knowing any more about what y is, all I could say is that's the derivative of y with respect to x. These two symbols mean exactly the same thing. Exactly the same thing. Now, we're going to, in some work we do soon, we're going to see things like this. dy dx times y. Okay? This means something totally different from this. What this last line says is take the derivative of y with respect to x, that's this, and multiply it by y. But what this previous line said was just take the derivative with respect to x of y. So how you write things using proper notation is going to be extremely important here, or we won't see any difference in these symbols. Okay? Just keep that in mind and pay attention to writing everything correctly. It'll really help you. Okay, so what do we mean by implicit differentiation? Well, we've been taking derivatives of functions, of finding the slope of the line tangent to the graph of a function. Remember, a function passes the vertical line test. But what if I don't start out with a function, an explicit formula for y in terms of x, like y equals sine x or y equals x squared? What if I start out with some equation involving x and y, like x plus y equal 3 plus y squared? It's difficult to explicitly solve that for y in terms of x. It could be done. Sometimes we start out with equations involving x and y where we can't solve for y. But solving for y here is a bit difficult. We'd have to use quadratic formula. And we'd have variables involved, 2 variables and not 1. So we use implicit differentiation when we start out with an equation involving both x and y, like this one. Now, the graph of an equation in x involving both x and y is some kind of a curve in the xy plane, like this curve. This is the graph of x plus y equal 3 plus y squared. You can go to Desmos or other function graphers, and you could Google how to get them to graph not functions but equations in x and y. This might be called an implicit function grapher. And you'll notice that if you have an equation in x and y, the graph is just some curve in the xy plane. Now, likely it'll flunk the vertical line test. This flunks vertical line test. There's a vertical line that intersects the graph in more than one point. But that's okay. In section 3.5, if you'll look in that section, you will see several different curves with names for these. For example, on page 215, section 3.5, number 29, you see a cardioid. You see that equation for the cardioid. It involves x and y. It's shaped like a heart. Number 30 on page 215, section 3.5, you'll see a curve called an asteroid. And you can look and see the equation for that. There's a lemniscate in 31 and the devil's curve in 32. If you also look on page 215, section 3.5, number 5 through 20, you just see a bunch of equations involving x and y. So, with implicit differentiation, we're given an equation involving x and y. Its graph is some curve in the xy plane. And what we're interested in doing is finding the slope of the line tangent to this graph at a point. In other words, we're still interested in finding the derivative of y with respect to x, so that at any point xy, we can find the slope of the line tangent to the graph, or the instantaneous rate of change. Now, why do we call this technique that we're going to learn of implicit differentiation, why do we call it implicit differentiation? It's because y is not explicitly solved for x, but this curve has a lot of functions implicitly buried within it, or implicit functions buried within it. For example, how about this? This is the top half of this sideways parabola. That part of the graph passes the vertical line test. So the top half of this parabola is a function. The bottom half of this parabola is a function. These are implicitly defined by this equation, x plus y equal 3 plus y squared. So what implicit differentiation does is it allows us to find the slope of the line tangent to any curve in the plane, as long as we know its equation, at any point. Okay? Let's stop here, and this gives you an idea of what implicit differentiation is. And we'll pick up with the next Pencast, where we teach you the technique of implicit differentiation.